Alright, so welcome back to particle physics and the standard model. This is lecture 39, and last time we saw how to obtain the number of real observable parameters in the CK matrix. Okay. We had already seen that generically you would have 6 phases and 3 rotation angles, but then we saw that even though you had some freedom to remove those phases using the U16 chiral symmetry of the mass terms, we found that if all the phases were equal, you can't really remove away, you can't really rephase using the chiral symmetry. Okay, you can't remove away that particular phase, right? And we saw how to do that. We parameterized the CKM phases in this way and saw that if there is a common phase phi, that cannot be really removed away using the U16 chiral symmetry. Okay, good. And that left us with one phase in the CKM matrix, correct? There were 3 rotation angles and one phase, and so we were able to parameterize the CKM matrix in this way, and that helps us also give us a convenient parameterization to report measurements, right. So, these are all inputs to the standard model which can only be obtained through measurements, and we saw what the rotation angles were and the CKM phase was. Okay. Also we saw yet another popular parameterization due to Lincoln-Wolfenstein written in terms of this lambda parameter, and at least the real part of the CK matrix looks like this, where most of the elements are seen to be almost diagonal, and the small rotation angles are dumped into powers of lambda in the off diagonal elements, okay, where lambda is 0.23, signifying that these are all small rotation angles, right. And I made a statement that we can only have this CKM phase if there are at least 3 generations. How do we know that? If we take 2 generations by once again parameterizing in terms of rotation angles and phases, we see that there is enough symmetry, enough chiral symmetry in the mass terms to remove those phases. Okay, you have a U14 chiral symmetry and 3 phases, and you can easily remove away those 3 phases without any problem. Okay. This is very crucial because we keep saying phase, but physically that phase is nothing but a parameterization of CP violation in the weak sector. Okay. And we just began to saw why having an e power I delta phase corresponds to CP violation in the Lagrangian. Okay. So, I started writing down the relevant part of the Lagrangian, and in this lecture we will continue with that calculation. Okay. And for that I have to tell you what the C operator, the charge conjugation operator, actually means in quantum field theory applied to spinors in particular. Okay. So, I am going to give you this, but it is up to you to go and check it. Okay. I am going to give you the definition of charge conjugation, and it is this. If I hit a left handed spinor with the charge conjugation operator, you do expect there to be some complex conjugate, but then you actually go to the right handed field. Okay. And it so turns out that you need a proper SU2 structure that turns out to be I sigma 2. Okay, which is also the Levi-Civita tensor, a 2 by 2 Levi-Civita tensor, correct? Okay, turns out there is a minus sign here, and then similarly if I hit the right handed field, I get this. Okay, so how do we know this is the correct operator? I am going to refer you to either Srednicki or Schwartz. Schwartz has a nice way of showing why this is so. Okay, look at these QFT books. Okay. Now let us inspect what happens to the mass term basically in the Lagrangian, right. So remember, this was the only Lorentz invariant way of writing a mass term. I keep saying this, right. You have to marry the left and right handed spinor fields. Okay. So just in case it is not clear, this is the mass of the fermion. So what do you expect when you hit the mass term with a charge conjugation? So there is no physical reason for why this should change, right. You expect this to be the same, right. So let us see if this happens. So this will give us confidence about the operator, then we will apply it to our particular Lagrangian interaction. Okay. Okay, and this will also help us understand some subtleties in the charge conjugation. Okay. So can you work out what happens if I hit this term with charge conjugation? Okay, and remember it is a multiplicative quantum number. So what happens now? I have a psi L dagger also. What do you think should happen? So nothing happens to the mass obviously, right. So let me pull that out. If I hit with charge conjugation, would you agree that this is the transformation? First of all, let me write out the simplest term. If I hit the psi r, what happens? Literally I just pull out the I sigma 2 psi L, correct. So I have that. Now what happens if I hit the psi L dagger? So I would get I sigma r transpose sigma 2. Agreed? If you do not, go check this. So now take psi L star and then see what happens if I hit charge conjugation. I should get a minus I sigma 2 star psi r, right, and then I take a transpose. So that is what I have done here. When I take a transpose, the sigma 2 goes to the other side, right. Okay. So all these details turn out to be important. Okay. That is always the case in field theory. Every little minus sign, every little transpose, you have to keep track of every little thing, but then they are all physically important. Okay. That is why you should never be frustrated by these tedious looking calculations. They are all super interesting. Okay. And while I was saying that, I wrote down the second term. Agreed? Again I hit psi L with C, I get the first term, and then I hit the psi r dagger, I should get the second term. Okay. This I am going to write as psi r t. What have I done here? I am just taking sigma 2 times sigma 2. Okay, and then I'm multiplying the I squares also. That sigma 2 times sigma 2 gives me what? The unit matrix, and then the I square gives me a minus, right. So I pulled out a minus now. So I just have a term like this. Okay, by the way, I should have put a star here. So there is a star in both the terms. Excellent. So this does not look like this, correct? This mass term does not look like this mass term right now, right? But they actually are the same, and here is how we are going to see why they are the same. Okay. I am going to expand this in terms of the spinor components. I am just going to call, remember there are two spinors, right? So this is literally the two components of the two spinor. Okay, and then I am going to label them A and B. Okay. If I do that, okay, let us call this equation star. Then the equation star is nothing but, I am just going to simply expand what is in there. Do you agree that there is a transpose? So, it is the psi r a psi l a star plus psi r b psi l b star and psi l a psi r a star plus psi l b psi r b star. Simple, right? Just took the transpose and multiply. Okay? Now, I am going to claim, okay, that this is psi l a star psi r a plus psi l b star psi r b, okay, plus psi r a star psi l a plus psi r b star psi l b. What have I done here? I have just switched these two terms, right, everywhere. However, notice that I have also dropped the minus sign. Why did that happen? That is because these numbers, right, psi r a, psi r b, okay, because psi l a, psi l b, all these numbers actually do not commute, they actually anti-commute, okay. That is what makes, that is one of the things that makes spinors really special. This is not just a 2 by cross, not just a 2 cross 1 matrix. The numbers that populate this matrix are very special numbers, okay. They are called Grassmann variables or Grassmann numbers. Okay. You need to populate spinors with Grassmann numbers in order to make fermion wave functions anti-symmetric. Okay. So, you should go and convince yourself of this fact that you need to have the degrees of freedom that you put down in spinors, Grassmann numbers, in order to actually, when you use them as wave functions, when you use these fields, they have to anti-commute. Okay. Alright, so that is a very important and very strange trait of spinors. Alright. Now, if you make use of that, then once again, what is this? This is still star, right? This is still star, the equation star. Then you will have no trouble seeing that equation star is still giving me, is giving me nothing but, I think I dropped an m somewhere, does not matter. Okay, so I will just put star over m. Okay, it is giving me nothing but this. Agreed? So, now I have psi l star psi r. So, that is just, so I am just basically hitting it with psi l dagger, hitting the psi r with psi l dagger, that is what it means. See, we recovered the mass term, that is what, you agree, right? This is the this was the mass term we began with, and then we ended up with the same mass term. So, inwards mass term is invariant under charge conjugation. Okay, excellent. Now, let us go back to the vector term. Okay. So, what about the vector term that we began with? What is the vector term? Here it is from the previous lecture, this term. Okay. So, let me apply C on, let us just take the first term. Okay. I am not going to take both the terms for now. Just to see how this goes, let me take just this first term and apply C on that, and I have W plus mu U will dagger sigma bar mu dl e power I delta. Okay. And once again I am gonna use these transformations, this set. What happens then? You shouldn't just follow along, okay. This is something that you should try to pause and work out by yourself. With field theory and particle physics, it's very important to work things out by yourself. Put pen on paper. Only when you work things out by yourself, you will understand what really these things physically mean. Okay. Otherwise, you're absolutely going to forget tomorrow. Okay. So, I highly recommend working this out, but I'm going to start writing down the answer. First of all, what happens to W plus under charge conjugation? Obviously, it goes to W minus. That's trivial, correct? Okay, so I'll just write that down explicitly. I put a minus sign out. I shouldn't have done that right away. Let's do it a little slowly. What happens to UL dagger? I'm just going to start writing. Okay, I have a sigma 2. All I'm doing is apply those transformations, the C transformations. Okay, so sigma bar mu, then I have another sigma 2, then I have dr star, and e power I delta just goes for a ride. Okay, then I'll put a minus. Why? Because I would have had two i's, right, just like before, just like in the mass term, and those i's multiply and give me a minus sum. That's all it means. Okay. Now, I am going to write down what this is, and I will tell you what properties of the Pauli matrices I used. This turns out to be nothing but W minus dr dagger sigma bar mu ur e power I delta. Okay. So, I will tell you what I did here. So, I used two things. Okay. What I did was I used first of all the fact that sigma 2 sigma I sigma 2 is nothing but sigma I itself if I is equal to 2. That is trivial, right? Because sigma 2 times sigma 2 is just identity, and then I am left with one more sigma 2, right? But it turns out to be minus sigma I for I equals 1 and 3. This is also trivial. Why? Use the anti-commutation relations. Okay. Or yeah, exactly. Use the anti-commutating properties of Dirac matrices, rather Pauli matrices, and you will see that I will have to switch the sigma I and the sigma 2, picks up a minus sign, sigma 2 square is identity. Okay. So, I used this. I also used the trick that we just made use of, which is Grassmann number anti-commutation. Okay. Good. So, that is why I was able to move dr dagger to the left and ur to the right using the Grassmann number anti-commutation. Okay. Now, I was talking about Cp, right. So, why don't I apply P also to this? Because I want to actually check the CP properties of this. Okay, I am going to take this object and apply parity to it, alright, and see what happens to that object. Okay, so I take the W minus dr dagger sigma bar mu ur e power I delta. Okay, that is literally this. Okay, so I am going to underline this for you. So this is literally this. What should happen now? How does the transformation go? W minus goes along for a ride. Now under parity I just flip the right and the left, correct? Agreed? So I have d L dagger sigma bar mu ur e power I delta. Okay. So what have I done here? Let me use yet another color. I have taken this object, applied CP to it, C and P one after another, and got back this object. Okay, good. So keep that in mind, and I am going to write down the CP transformation of the entire term that we had here, this entire term, right? Because my claim was under CP this is actually not invariant, correct? So let us see if that is true now. So under CP that term, okay, up to some coupling constants was nothing but sigma bar mu dl e power I delta plus w mu minus dl dagger sigma bar mu ul e power minus I delta. That is the crucial part here, right? When we wrote down the Hermitian conjugate we had a minus here, correct? So let us see what happens under CP, and I am going to write this down in a certain way. Okay, I am going to first write down the CP conjugate of this term, second term. Okay, what is that? Under C W switches sign, under P it does not switch, right? So I am going to write for this term it is W mu plus, and then what happens? By analogy with what is going on here, it is a UL dagger sigma bar mu dl e power minus I delta, right? This minus. And similarly, okay, so let me just be clear, this is that, okay, and then this term is going to transform as W mu minus dl dagger sigma bar mu. That is what we saw here, right? When you started with the UL dagger you ended up with DL dagger, UL e power plus I delta. This became a plus. So it is clear, right? So to avoid clutter I am going to remove these arrows. Now isn't it clear now that under CP this term has changed completely? What is different now? These, right, these terms are the same, correct? These two are the same, these two are the same, but the face has completely flipped. Correct? So these two terms are clearly not equal to each other. In other words, right, if the face delta is non-zero, CP is violated. Okay? And this is where the statement that if you have more than or equal to 3 generations or more than 2 generations, it implies CP violation in the weak sector. See, all of this, remember, came down to us after symmetry breaking. This is why symmetry breaking is important. You cannot understand the phenomena that the standard model gives rise to if you don't know, if you don't have some sort of symmetry breaking, which turns out to be spontaneous symmetry breaking in our world through the Higgs mechanism, correct? All of this is interconnected. Okay? So, well, the converse here is that trivially, if delta is 0, what happens? If delta is 0, these two terms are equal, right? E power I 0 is 1. So, clearly those two terms are equal and CP is not violated. Okay. Excellent. Now I am going to ask, this is, okay, I am going to give this a name, okay. We have already mentioned it a bit. Let me take, let me take just this term. This is what I would call a flavor changing, okay, charged current. Why is that? Clearly it is flavor changing, right? The U goes to D. That always does, that always is forced to happen because you are interacting with a W boson which is electrically charged, right? And this is a current because you have to think of this part, that part alone is a current. Okay, so you have a fermion number flowing from the UL dagger to a DL. So that is what people mean by a current, right? And then you have some Lorentz structure in between. In this case, it turns out to be a vector structure, right? Why is it a charged current? That should be obvious, right? There is a charge to this entire UL dagger DL structure, which is in this case it's a minus sign. That's what is eaten up by the W plus boson. So on the whole, it's fair to call this a flavor changing charged current, correct? If that is the case, shouldn't there also be a flavor changing neutral current in the standard model? Right? So this is sometimes called, well, most of the times it is called FCNCs, flavor changing charge neutral current. Okay. What about those? What about those Lagrangians basically? Okay. And I am going to show that you actually do not have flavor changing neutral currents at the tree level at least. Okay. For now ignore this image, we will come back to this in the next lecture. So I am going to wrap up this lecture by writing down some terms that to show why you do not have flavor changing neutral currents in the standard model. Okay. Let us see where these things even come from. See, in the flavor basis, I have okay, ULI dagger, in exact analogy with the W boson terms, the W boson interaction terms, I have this, correct? I am writing this in a very deliberate manner. In particular, the I index is a flavor index, okay. And the I repeats here, correct? It is a repeating index that shows that the up quark interacts with the up quark with the Z boson as the mediator, the down quark interacts with the down quark, the strange quark interacts with the strange quark. There are no flavor flips here. That is what we saw with the W boson also actually, right. The first generation interact with the first generation in the interaction basis, right. The interesting thing is what happens in the mass basis, okay. That is what led us to the CK matrix, correct. So, I am going to stop here and ask you to go and rotate this flavor basis Lagrangian into the mass basis and check for yourself what should really happen. Go back to the Yukawa couplings and rotate to the mass basis, take your rotation matrices and check whether you introduce another something called something like a CK matrix for the Z boson sector also, okay. So, I will leave you there, see you in the next class, thank you.